Joining us today for the second webinar in RSK's Creating a Buzz series, which focuses on different aspects of electricity transmission grid infrastructure development. Today's webinar focuses on how RSK group companies employ digital tools to lower risk and speed up delivery of HV substations, which are a critical component of future transmission grid infrastructure. Before we get going, I'd just like to quickly deal with a few minor housekeeping issues. So all attendees' microphones are automatically muted throughout the webinar, and during the presentation you can post questions online, and there'll be a Q&A session at the end of the presentation. You'll see the question mark button up in the top right of your screen. If you click on that, you'll get a panel to add questions, which we'll be reviewing through the course of the presentation, and we'll answer as many of those as we can once the presentations are over, time permitting. Shortly after the webinar as well, you'll also receive a link to a short survey, and we'd really appreciate it if you just take a few seconds to provide some feedback so that we can improve future webinars as much as possible. So just to introduce the smiling faces on the screen, my name is Roger Emsley. I'm head of the energy division at Nicholas O'Dwyer, which is an RSK group company. And I'm joined today by three expert speakers. Paul Coleman, who is head of digital delivery at Nicholas O'Dwyer, Keris Lowe, who is a senior design engineer at Navitas Engineering, and Neil Skelton, who is an associate director at Nicholas O'Dwyer and leads our substation civil design team. So what we're going to cover today, we're going to kick off with just an introduction and setting the scene, just to explain why this is relevant, why HV substation development is relevant, why we need to deliver them at scale. We'll do a brief introduction to the two companies that you have on the call today, Nicholas O'Dwyer and Navitas Engineering, both RSK group companies. Paul will take us through our approach to digital delivery and where we are on the journey of developing our digital delivery capabilities. And then we'll get into some specifics of substation design, looking first from the electrical perspective, which Keris will take us through, and then from the civil perspective, which Neil will take us through. And the focus of the overall presentation is these digital tools that we use to manage the civil electrical interface in substation design. And then finally, we'll wrap things up and we'll get into some questions. So we're all going to turn our cameras off now for the presentation itself, and we'll turn them back on again when we get back to the Q&A section of the presentation. So jumping first then into the introduction and why this matters. We're very much at a point where the energy transition means that we need a step change in grid delivery and grid infrastructure delivery. This is true across Ireland and the UK and the wider world, really. But if we look at the Irish and the UK context a bit, in Ireland, in the next 5 years, there's a plan to deliver more than 70 new and uprated HV substations. That translates to roughly 2 to 4 billion euros over the next 5 years, just on substation infrastructure in Ireland. And this is part of the wider grid infrastructure investment in Ireland of up to 19 billion over the next 5 years. Big numbers in an Irish context. On the UK side of things, we're looking at 130 transmission substation projects, or about 8 billion pounds spent just on substation development over the next 5 years. And that is part of the wider 35 billion plan to develop the UK grid infrastructure over the next 5 years. And just to put that into context, that's about 5 times the historical rate of infrastructure development in electricity grids. So it really is a massive step change. And just to understand that from a wider European context, across Europe, we're talking about 500 billion being spent on electricity grid infrastructure over the next 5 years. So it really is a massive scale of infrastructure development, and delivering this scale of infrastructure at pace presents real challenges. It's a lot more than has been done before. It means the supply chain is going to be stretched. It means that we're going to be upgrading a lot of existing sites. The complexity of sites is going to get higher. The complexity of projects is going to get higher. And so it's vital that we can deliver projects efficiently, coordinate between disciplines, manage risk, and make sure that substations can be built without design issues. So overcoming these design risks, enhanced design is essential at an early stage to ensure that the projects are de-risked and optimized for buildability, which is where our integrated civil and electrical design services add value, using enhanced BIM models to effectively manage that civil electrical interface and produce clash-free, construction-ready design. So today we're going to explore how Nicholas O'Dwyer and Navitas Engineering benefit from the use of digital tools to manage and support the rapid build-out of essential grid infrastructure to help deliver on these massive numbers that you see on the screen. So just to introduce our two companies before we get into the presentations. First of all, Nicholas O'Dwyer. So Nicholas O'Dwyer is headquartered in Ireland. They're one of the largest engineering, environmental planning, and project management consultancies in Ireland. And we've been part of the RSK group since 2021. But we've been involved in the energy sector a lot longer than that. Our history dates back from 1932, when we started out in water and wastewater, but we got involved in the energy industry about 25 years ago, pretty much at the time that onshore wind was really becoming a factor in the Irish energy landscape. And we got involved in some of those early projects. But we have very much a global presence. We're very proud of now having over 300 employees in 8 offices, but representing more than 50 nationalities. We've worked in more than 50 countries. So very much international expertise across our business. In terms of the energy experience that we have, we've worked on a lot of energy infrastructure, including pipelines, grid, and substations. We've designed over 15 HV substations in the last number of years, and we also work on the generation side of the industry in PV, onshore wind, and energy storage, geothermal, and district heat. Our company is divided into 7 divisions. So we cover 7 market sectors across water, wastewater, transportation, climate resilience, energy, environment and planning, and building and structures. And our HV substation design expertise very much cuts across our energy division and our buildings and structures divisions. So just to give a very brief snapshot of our substation design services, our offering is broad, covers the full project lifecycle of substations, from right at the beginning with the flood risk and climate resilience assessments, planning and permitting, and concept and feed design, all the way through the various design phases to detailed civil and structural design across all aspects of the substation site. And then wider services related to project management, PSDP in Ireland, and principal designer in the UK. And of course, what we're here to talk about today is our BIM and 3D capabilities and how that feeds into our design services. And then working with other RSK companies, we can cover all the disciplines required for the design and delivery of HV substations. So one of those companies is Navitas Engineering, who are specialists in the electrical design of the substation. So now I'll hand you over to Keris, who will introduce Navitas. Keris?
Good afternoon, everyone. My name's Keris Lowe. I'm a senior electrical design engineer at Navitas Engineering. I've worked there for about 5 years. Prior to that, I was in oil and gas and the battery energy storage solutions. So who are we? We're an electrical design consultancy. We specialise in the rail and the energy sectors across the full lifecycle of the asset. We work with clients, suppliers and stakeholders to maintain high quality and efficient design output. We work across the UK and internationally. So recently we completed a job in Buenos Aires working on the Line B power upgrade. We've also done some modelling support in Rio Tinto for Australia and are currently undertaking some R&D in Hungary. So where do we sit within RSK? So we're a business unit operating within the Octavius Group, who are a transportation and construction maintenance company, following a successful merger in 2024. We work closely with the rail sector within Octavius. However, we also operate across the following areas. So this is just a highlight of some of our capabilities within the rail and energy sector. So with repeat customers, we've successfully worked within system planning and network modelling within the rail industry. We've developed safety cases We're at the forefront of electrical safety management, electromagnetic compatibility and testing, and as I previously mentioned, we're working on R&D and some innovation. And here's just an overview of some of the customers we currently work with. However, for the purpose of this webinar, I'll concentrate on the work that we do within the energy sector. So from concept and feasibility studies, network analysis and EMC and RAMS assessment to the detailed design of grid, primary and secondary substations, we provide high quality design delivery across the life cycle of the project. We work closely with our civils designers and other disciplines to provide an efficient and safe design. I'll now hand you over to Paul.
Thank you. Hi, my name is Paul Coleman. My background is I'm a civil engineer and project manager, and more recently, my role in Nicholas O'Dwyer is that I am the head of digital delivery. And today, I'd just like to go through a bit about what digital delivery is, the journey, I suppose, that Nicholas O'Dwyer have been on in terms of improving our digital services and improving the way that we do things digitally, and how that's applicable to substation design and the kind of tools and methods we use and the approach that we take. So that's what I'll go through now. And go on to the next slide, please. Yeah. So just to describe what digital delivery is, and it's a term that's used. Different companies use different labels for this. You sometimes hear digital engineering and other terms. So what it mainly focuses on really is three things. One is BIM, and that's the 3D models and the actual delivering of BIM models and actual designs. But obviously a large part of BIM is also the processes and the procedures that are in place to make sure that those digital tools are used in the correct way to get efficiency of what we're delivering in terms of design and construction. We're also in digital delivery, we're responsible for all of the hardware and the software that we're using, which includes all kinds of equipment these days, including, VR and drones and all kinds of stuff. So that's what we're responsible for. And also for our general digital transformation, including the use of AI where applicable. So that's really about just making sure that the process and procedures, again, that we're using are getting the best out of technology and getting the efficiency that we need in our design and our overall business management. So there are kind of three focuses of what our digital delivery team work on, BIM being, the large one that I'm going to talk a bit more about today. So I just go to the next slide. So look, Nicholas O'Dwyer, as mentioned, we've been around since 1932. We've always kept up to date with the most cutting edge technology that are out there. And this is all the way back from when Nicholas O'Dwyer himself was using drawing boards and pen, paper, etc. To the days when we moved into using CAD and, computers, basic processing, Windows, etc. Through all these phases, through to where we're at now, where we're using much more advanced digital tools. In particular, regarding the BIM space, you're talking about using 3D modeling, common data environments, digital tools for markups, all kinds of things that I'm just going to talk about a bit more about what we use and the approach that we take to using these tools and the approach that we'll take regard to substation design to make it the most efficient process possible. So next, please. So the basis of it all really is 3D models. Okay, so from the very start, when Revit and 3D CAD came out, Nicholas O'Dwyer were using these tools, and we were some of the first to ever actually use these tools in the design sphere, infrastructure design. So we've been using these for a long time. Where we really get the most out of it is identifying things like clashes, obviously, things like visualizing our designs, splitting models up and allocating to different disciplines so that they can all work together and then come together in a federated model and understand how we can all work together in terms of collaborating together. 3D models are wonderful for, making changes. Everyone knows design projects are constantly need changes and updates as things go and new constraints are identified. When you're doing it in 3D, it's much more easy to make a design change. You move things around. It may take a few more, small bit of time extra to set up originally, but once you get into the design, it's a hugely beneficial tool. And 3D models are the basis of it. We also do deliver 4D models where time is added. And they obviously hugely advantageous in terms of sequencing the work and planning the work virtually before you actually build it on site. And there's huge advantages to that in terms of avoiding clashes and of construction activities, etc. We also do offer some 5D services in terms of adding cost to the model and also adding carbon values to the model, so you can actually use your 3D model to identify your carbon footprint and your costs as they develop as the design progresses. So that's the foundation of things. I think a lot of people are doing this, but I would say, it isn't always. You might think in this day and age everybody is using 3D models, and that's kind of obvious, but there are a number of designers still out there using CAD and various other tools out there. So we really heavily gone all in on using 3D models from the start. Next slide, please. Obviously, as part of that, something we really need to focus on, in particular regarding the very constrained sites that often occur at substations, is clash detection. So identifying where the services, and particularly the buried services, but obviously the above ground services as well, where they're likely to cause an issue of construction due to a clash. And that's not always easily identified on 2D when you're using it in CAD. It's just you're looking at sections, you don't always spot clashes. So by identifying processes and using clash detection, we can identify where the clashes are, resolve them before construction starts, and with associated benefits of efficiency of design and construction. So that's clash detection. Neil might talk a bit more about that later. Next slide, please. So just to be aware, we are, anyone that knows BIM, I suppose, it's based on a standard, an international standard called ISO 19650. We have had those processes and procedures associated with that standard in place. It used to be PAS 1192 for over 10 years. We've been certified by the British Standards Institute since 2019. And we implement these procedures on our projects. People will have seen things like file naming, common data environments, delivery plans, all of that good stuff that comes with delivering BIM and getting the efficiency from that. We also happen to offer this as a consultancy service separate as a company offering if other companies or clients need assistance with implementing BIM. So that's just a touch on our ISO 19650 cert. Next slide, please. At the core of it all really is managing information. And, any of these projects, in particular substation designs, they have loads of different parties all needing to work together. This image here shows the traditional ways of sharing information, where everyone is sharing information one-on-one, firing emails left, right, and center to each other, whether it's the client, the engineer, the contractor, subcontractor, or it could be, the different design disciplines, civil, structural, mechanical, etc. Often in a very fragmented way. So the idea of centralizing everything in a common data environment is kind of key to the services we offer, and that's usually using ProjectWise, but we use other tools as well there. Next slide, please. Another thing, I suppose, where you're getting more advanced in terms of technology use is we have a number of different VR headsets. And what we can do when we've modeled it up in 3D is put on the VR headsets, walk around the model virtually. And it's great for visualizing things, spotting health and safety errors, identifying bits that just don't look right when you actually are walking around and seeing them. You can see here one of our employees was using it on a model and he's marked up. You can mark up things, put a circle around them. You can identify an issue there. You can then allocate that issue for someone to resolve. So it's a nice little tool that we also use in terms of the more advanced use of technology in our design process. Next slide, please. So look, I suppose ultimately, there's plenty of tools there. I didn't even mention, like, we have drones and we use point clouds, and there's a whole lot of use of technology. But ultimately, it really means nothing unless you get the balance of people, process, and technology right. And that's where we really want to come in and, you know, hopefully offer something with a bit more focus than perhaps others do in terms of this mix. It's all very good having the technology, but unless it's used in the right way, it will not get you the benefits that you want, okay? That technology has to be used within a process that facilitates the technology and allows, you know, the proper management of things using those tools. And I think it's quite clear it would all fall apart if, you know, people weren't trained up, the people didn't understand the process they're working on. So by having those well-developed processes that we know create efficiency of design, we can roll them out on projects, and it certainly makes it repeatable, and it certainly guarantees that efficiency in terms of delivering the technology, because it's not always about the technology. It's about the use of it, where in particular our digital delivery team come in. And that couldn't be more evident than in where we need to collaborate between stakeholders, do coordination, clash detection, sharing information. Like, if the basic thing of sharing information can be a huge issue on projects where people don't know what the latest version is, they don't know what other people are doing, all kinds of issues occur there. And ultimately what it is about is the design efficiency. Okay, if you can get the benefit of this technology, the people are trained up in this technology, there are huge benefits in terms of design efficiency. And ultimately, the quicker and more quality design you can produce, ultimately leads to cost savings. And none more so than in the construction phase, where things like clashes are identified. You can do virtual rehearsals using the model. You can identify all kinds of things virtually before they happen physically. And that's, you know, one of the big focuses and benefits that we like to bring with our digital delivery process. So I might leave it there. Available for questions at the end, and pass you on to Keris. Thanks.
Thanks, Paul. Okay, so now we're going to look at the intricacies of substation design and how electrical design requirements drive a need to integrate with civils in a BIM model. So the first thing we do when we're designing a substation is to assess the existing conditions. So we need to confirm if there are any existing utilities in the area. Is there any existing infrastructure? Are we enhancing a substation, or are we starting from scratch? If it is a new connection point, then where would this be located? I'll leave the ecological aspects to Neil, who'll touch on them later. However, one thing that we look for from an electrical perspective is the soil resistivity testing for any future earthing design. It's also important for us to have a baseline EMF and EMC measurements to ensure that any future design complies to industry standards. When looking at feasibility of a possible new sub, we need to consider the type of substation and the compound layout. A 400 kV substation, for example, will have a larger footprint than that of a 132 to 33 kV sub. Likewise, internal switchgear occupies a smaller footprint than that of external equipment. Feeding arrangements and staging also require early consideration to ensure that supply is maintained during the construction stage. When we move from feasibility to detailed design, client requirements really become more prevalent. So we need to look at what type of protection and control is required. This is the point where collaboration and civils designers and other disciplines become essential. When looking at equipment type and location, we need to consider cable routing and entry. Does the equipment require additional cable support? Can we maintain the clearances that are mandated by the utility standards? Appropriate separation between equipment, i.e. the separation of transformers and switchgear and battery chargers, to name a few. One of the main areas for clashing is the M&E requirements of a substation. So this comprises a minimum of HVAC, lighting and fire systems. When we work with the civils designers, this would be integrated into the combined model in order to capture the space occupation of this equipment and any potential clashes. As an example, here we have a 400 kV substation at Burwell, Maine. You can see on the right-hand picture behind the large blast wall is where the 400 kV transformer is located. The equipment in this substation requires quite a large footprint when comparing it to that of the 132 33 kV grid at Burwell. Here we see the supply coming into the step-down transformer on the bottom left picture. On the right-hand side is a good comparison for internal versus external switchgear. So the building in the top right picture is housing the internal switchgear, and it's got a much smaller footprint than that of the 33 kV external switchgear you see at the bottom picture. Another combined consideration is the cable entry for the equipment. So here we see high-level connections to the 33 kV GIS breaker, which would require additional cable support. The image below is of a 132 kV transformer and its associated cable support. Alternatively, we have an indoor 132 kV double bus bar, which can accommodate bottom entry cable termination utilizing subsurface cable routes. So how does BIM modeling come into it? A BIM execution plan is essential to outline the policies, the processes, and the workflows, all stored in a common data environment that Paul has just touched on. As designers, we either align with an existing client BIM platform or adhere to our own developed plan in line with the client requirements. BIM is about data integration. Every element within BIM model contains rich information alongside its physical geometry. For example, a feeder cable route isn't just a set of lines. It's an object that can be programmed with specific material properties, dimensions, cost data, manufacturer details within the model libraries themselves. This can be used to directly plan logistics, estimate costs, and sequence construction, as Paul has already mentioned. The biggest challenges for creating these intelligent prototypes of physical and electrical design of a substation are creating the 2D and 3D libraries of equipment. We're currently using CAD tools, which were initially designed for use in the architecture and manufacturing industries and need a little bit of tweaking, shall we say. Surveys can be used to improve the outputs. So you can do LiDAR scans, which can be used to develop 3D renderings of existing equipment or new equipment. Other surveys can be incorporated into these models, such as GIS surveys, geospatial mapping, or points cloud outputs. We actually know that currently the government is developing a tool that is storing buried services data from all utilities within a central database for access for future projects. Here we can see what a point cloud rendering of a substation looks like when compared to that of a 3D model that's been built within Bentley. So substation layouts can be built in 2D and 3D, incorporating things such as structures and foundations, the cable routing as we've touched on, bus bars and connections, earthing systems, and many more. Building layouts capture the M&E requirements previously mentioned, cable management systems, and secondary equipment. Once the model is complete, we're able to extract reports such as wiring schedules or bill of materials directly from this model. By building rules into the common data environment, we can extract clearance verification, EMF and lightning protection reports, earthing system studies, lighting and HVAC modeling, amongst other things. The important thing here, as Paul has mentioned, is to maintain the workflow and version control. Internal training across CAD tools is essential. Knowing how to manage the data and generate templates within the shared environment is critical. A BIM model is only as good as the engineers utilizing it. The two BIM platforms we commonly work with are Autodesk and Bentley. For Autodesk, you can have a software called Recap Pro, which pulls points cloud information into a combined Revit, which can then produce a 3D model of an existing substation. AutoCAD Electrical can generate the schematics and schedules utilizing equipment libraries which have been integrated into the CDE. Navisworks then runs the simulations and design checks. Neil will show you a model on Navisworks, which Nicholas and I have created recently following my section of this presentation. An alternative to Autodesk is Bentley. So context capture can convert GI scans or LiDAR into a 3D point cloud. This can then be used to generate the model. Electrical systems design software creates the equipment models themselves. MicroStation can then be used to build models of new equipment that's going in. These models pulled into ProjectWise create the foundation, and then Open Utilities substation design is used as an error check to maintain and enforce utilities standards. An AI integrated tool is currently in development, expected this year, which will be able to link intelligent objects to part space. The tools to the right of the spider graph for the Bentley model are the XGS lab tools, which allow simulations such as earthing, lightning, EMF, and allows you to output cable schedules and BOQs. So SBS is a company that have developed a 2D and 3D substation design tool that pulls in the 3D modeling of primary and secondary equipment into their substation design suite, which they abbreviate to SDS. This will soon be replaced by the BIM substation designer in 2026, which has this AI integration. SDS substation design software is based off of Autodesk tools, which use Inventor and Revit and AutoCAD Electrical. The 3D models can also be pulled into Inventor to create a 3D model library of primary and secondary equipment for future uses. Design rules and checks can be built into Revit through the Navisworks design collaboration. Workflows or assurance checks assigned within the construction cloud, including publication of PDFs from the 3D model into the 2D drawings. Currently, this allows SBS to populate client requirements and create a model with valuable outputs and deliverables much more efficiently. So here we've just got a few examples of some of the models that we've built recently when adhering to the BIM processes and working within a common data environments with our sort of companies that we've been working in collaboration with. So on the left-hand side, we've got a triple pole disconnector that was designed at Boreham Wood. On our top right, we have an ABB SMOS outdoor switchgear. Below the SMOS, you'll see a return conductor bus bar where we designed interlocking within a restricted space. So the BIM model was really helpful to work out the clearances that we required for this. And then just to the right of it is the associated cable routing. So as you can see, it was a bit tricky. We had to make sure we were not clashing anywhere with that. These are just a few examples of where modelling has allowed us to visualise the proposed works and undertake the accurate detailed design stage and preempt clashes before they occur. So although BIM can make designs more efficient and accurate across disciplines, there are key considerations and limitations we need to consider. From development of the programs which feed into the common data environment to the utilisation of shared data, such as the enterprise asset management outputs, we require verification and validation. The key limitations that we've found as a business are inconsistent use of CAD tools across vendors. This paired with varying standards and procedures across clients can make integration difficult. AI tools are in an area are currently underdeveloped, however, we do see them improving. And finally, a reluctance to share models between utilities and vendors can result in duplicated effort in recreating models of equipment. With all this said, between the electrical and civils and other disciplines, it allows for a more efficient model, capturing the client's requirements and highlighting early and possible design issues, and is beneficial to any design process. I'll now hand you over to Neil, who'll talk you through the civil design of substation and integration of digital delivery.
Thanks, Keris. My name is Neil Skelton, Associate Director with Nicholas Dwyer. I'm a chartered engineer with 20 years experience delivering substation projects from renewables through to 220 kV transmission infrastructure. And today I'm going to focus on the civil side of substation delivery, where the key risks lie and how we use digital delivery to manage those risks early. So why civils are often the risk. Well, electrical designs define the function of a substation. It can often be the civil design that introduces the greatest delivery risk. From a civil perspective, we're dealing with limited space, uncertain ground conditions, and a high density of infrastructure below ground, like drainage, ducting, earthing, and utilities, which all needs to fit within tight corridors. And that's often compounded by existing buried services and environmental constraints, such as flood risk and pollution control. A common issue is late-stage interface clashes between the civil and electrical designs. And when those aren't fully aligned, we see that problems emerge on site, leading to redesigns, delays, and cost. And our approach at Nicholas Dwyer is to address that risk upfront through digital delivery. Next slide, please. Thanks. Our role on substation projects goes beyond producing drawings. We are effectively defining the physical environment that everything else has to fit in within. That includes site layout development, level strategy, drainage, and the coordination of underground services. We also manage the interface between how below ground infrastructure with structures, buildings, and electrical equipment, working closely with multidisciplinary teams to ensure that everything aligns as the design develops. In essence, our role is to bring these elements together into a coordinated, buildable solution. Next slide. So digital delivery fundamentally changes how we do that. By working in a federated model environment, the civil, electrical, and structural designs are coordinated together from an early stage. That allows us to identify and resolve clashes before construction. It reduces redesign, improves efficiency through faster iterations, and ensures that the design is genuinely buildable. And the key benefit is increasing certainty, both in design and delivery. Next slide. So getting it right early. On substation projects, particularly at a transmission level, decisions made early in design have a disproportionate impact on delivery, we find. So once layouts are fixed, making changes become difficult and costly, and our approach reflects the principle of think slow, act fast. We're investing time early to test out layouts, levels, drainage strategies, all within a coordinated model. And this allows key interfaces to be resolved upfront, resulting in a design that is coordinated, buildable, and supports efficient construction. Next slide, please. So a key part of making this approach work is collaboration between civil and electrical teams. The highest risk area on substations are typically at these interfaces. And by working in a shared model environment, all disciplines can develop designs in parallel with full visibility of each other's constraints. Coordination becomes continuous, supported by regular model reviews, where layouts and interfaces are actively tested and refined. This ensures issues are resolved before they become embedded in the design, improving confidence and reducing risk during construction. So now I will show you how this actually works in practice, how we've used it in practice, and I'll show this through a live project model. So this is a 220 kV substation in North Dublin, which is connecting directly into the transmission network and supplying a large data center via 20 kV distribution. This federated model I'm sharing here brings together civil, structural, and electrical design, and is being used currently as a live coordination tool. It's a constrained site with high density of infrastructure, particularly below ground, and I'll just show a few examples here of how we've coordinated that through this model. So this first example I'm just showing here is drainage coordination, which is often more complex than it first appears on substation projects. This part of the site showing the drainage network for the transmission operators GIS compound. And here we need to manage surface water runoff from the GIS building and surrounding infrastructure while integrating pollution control, all within a very tight and constrained footprint. Key challenge here was that this network had to tie into the adjacent data center's attenuation system. So we had to coordinate closely with their design team using this model and align discharge levels and coordination points. And at the same time, we had to coordinate a significant east to west ditch diversion culvert through the site, with our drainage network passing over a very shallow box culvert, which we had to design. If I move now onto the customer compound, the constraint site provided even further complexity. With the customer compound, there's road drainage had to be coordinated around significant MV and LV and ducting requirements, working around a large culvert, the same ditch diversion culvert here, while the transformer bund drainage had to be coordinated through quite dense AIS equipment and transformer area. In addition, the oil containment strategy for the 4 transformers required a full retention separator as a secondary safeguard, which further introduced space and layout constraints. Now, using this model, we were able to coordinate these systems in 3 dimensions, identifying clashes early and refined the layouts before they were fixed. The second example I'll show here is where typically we see the greatest value in these models is in the coordination of underground services. Here in the customer compound, we're dealing with MV, LV, and comms ducting running between the transformer and AIS equipment and the MV switch rooms. The challenge here was the routing of all these systems through a very constrained zone while maintaining the required electrical clearances, particularly where they crossed over the large fixed culvert. And this created a high congested area where vertical and horizontal separation really became critical. Using this model, we could test routing options, resolve crossings, and agreeing clearances with the electrical team early, which ensured that the layout was both compliant and buildable. At the GIS compound, the design mainly focused to the high voltage ducting connections into the substation building. Here, the primary challenge was really aligning the duct spacing, the depths, and routing these with electrical design requirements, particularly cable rating assumptions and installation constraints, while interfacing with the building structure here. This required close collaboration with the electrical designers to ensure that the civil layout supported the performance required of these cables. The third example I'll share here are around levels and the overall buildability of the site. That developing the level strategy is fundamental on a site like this, as it underpins drainage, access, equipment installation, and how the site is ultimately constructed. Here we need to establish a level design that tied the GIS compound and the customer compound while integrating these with the adjacent data center. And that resulted into a split level site formed by a retaining wall shown here. And this brought its own challenges with crossing services. However, we used the model to test the relationship across the site, ensuring that the levels fall and tie-ins all work together. So across these examples, the model has allowed us to resolve complexity early in a controlled environment, and that resulted in greater design certainty, improved coordination, and a smoother construction phase with fewer surprises. For us, digital delivery is embedded in how we approach substation design, enabling us to manage complex interfaces and deliver projects more efficiently at scale. So that's it for me, and thank you very much. I'll now hand back over to Roger.
Good stuff. Thanks very much, Neil, and thanks also to Clarice and Paul for taking us through those sections. And just to wrap up before we get to the Q&A section, I think there are a couple of themes that emerge from this from the various presentations and presenters that you've heard from. But really, I think it's important at the transmission infrastructure level to realize this is a once in a generation opportunity to build grid infrastructure, and that substations are really a critical part of that. But as the scale and the speed of execution ramps up, never been more important for design excellence or to have design excellence. So we've heard from Navitas, who are experts in electrical design. We've heard from NOD, who are experts in civil and structural design. And we've heard from how our digital tools are helping us to coordinate between those disciplines and deliver more efficiently. But But this coordination and efficiency is only getting more important and more vital. There isn't the time to correct errors if we're going to roll out at the speed required. And there's also a need to identify all those issues as early as possible using the tools that are at our disposal. Of course, today we focused on the civil electrical interface, but this coordination extends well beyond just those two main disciplines. There's the multiple different disciplines involved in substation design, and the use of these digital tools enables us to increasingly seamlessly integrate all of those different disciplines to drive success in substation delivery. Now, across the RSK group, we provide all of these different services, which are stitched together both by our digital tools and our project management expertise, which ensures that we can assist in delivering HV substations at scale over the next 5 years. So please, thank you for listening. Please don't hesitate to get in touch with us if you would like to know any more. The slides will be posted on our website, and also you can see the presenters' contact details there. Feel free to reach out directly if you have any questions would like to discuss more. So that concludes the formal presentation. We've got about 10 minutes left for questions. So we're going to turn our cameras back on now so that you can all see our pretty faces again. And I will feel free to add any additional questions that you may have. And so I might kick off. I think the first question we've got here that's probably relevant, and Paul, I'm going to combine two questions and come to you with a sort of a bit of a double header. But what approach do we take to keeping up with developments in the technologies? So, you know, Keris made the point that the BIM model is only as good as the engineers using it. But how do we ensure that our engineers and technicians can make the best use of the available tools, so we're not constantly just iterating and updating the tool? And I suppose a related question is there a risk that we're heading towards a world where there's over-reliance on the digital tools? So I suppose that's similar to the idea that if you give young kids calculators, they might never learn to do arithmetic. So how do we incorporate these tools into our design process to make sure that we're leveraging the skills of our engineers as still the primary point of difference in substation design?
Yep, thanks, Roger. Yeah, I suppose it comes back to really what I was talking about earlier in terms of that correct blend of people, process, and technology. You know, the technology is always advancing. At Nicholas O'Dwyer, we're constantly testing new technology as it comes up. And we make a decision one by one as to what the best technology is for the particular case. And when I talk about technology, it's usually tools focused around any particular activity. We are obviously aware that when you implement a new tool, it comes with that process and people part, which is around training and configuring them. So there's constantly these new tools coming out, and you go, okay, well, let's implement that on this project. And you realize there's a lot of time and effort needed to configure that particular tool to be used in the right way for that particular project, and then make sure everyone is trained and up to date with that. So we really need to focus on the kind of process and people part of it, because there's constantly new technology coming in, obviously with various different AI tools available as well these days. So we need to keep an eye on that. I mean, ultimately, when people are coming to us, you know, Nicholas O'Dwyer and Navitas, they're coming to us for our people, our expertise. And we can never rely on our tools to do the work that our people are doing. You know, obviously a bit further with the use of AI, people are maybe leaning on advice from AI, large language models, etc. But really, you know, it's about the people. It's about using the tools in the right way and having the right tools to do the work that we need to do in the most efficient way. And sometimes tools can get in the way of things. You know, it can happen. as you kind of allude to that question. But yeah, sometimes, you know, the wrong tool is selected for the job, or maybe it's, you know, too much of a big process for something that might be quite simply done without getting into a convoluted tool to do the project. So look, we're all constantly looking out for new ones. Just like recently, we're focusing on different methods for doing design reviews, 3D model reviews, allocating tasks when the review is done to different people. There's a whole load of different tools out there to do that, some more advanced than others. But in the end, as long as somebody picks up that design, that you know, whether it's a drawing or whatever, you know, really the important thing is they do the review correctly, even if it's picking up a pen or a pencil and doing it on a pad or on a printed drawing. You know, it's not the most advantageous way, but it's really about making sure we're continuing to deliver the service as efficiently as possible. So that's something we need to focus on.
Thanks very much there, and Paul. There are actually a couple of questions here. It wouldn't be a modern webinar if we didn't have AI mentioned, but you also talked there about the integration of different AI tools. Maybe this one best directed at Keris, and how you see the development of AI affecting the use of BIM software across the design process, and how you're seeing that evolving.
I think, yeah, it's a tricky one because AI is ever changing and ever evolving. I mean, at present, the BIM processes are primarily digital documentation and coordination of workflows with the models integrated. And it's for more optimized decision-making systems. I think we're already seeing steps towards AI integration with SBS and the Bentley BIM substation designer, but I would anticipate AI basically making the design of the models and the outputs of the schematics easier to adopt and faster to initiate. And we could potentially move from clash detection once the models are created to sort of possibly being able to preempt the clashes at earlier stages. But ultimately, it comes back to what Paul said, in that AI will only speed up the modeling for us, and it's still down to the engineers to validate and verify the outputs.
Yeah. Okay. I mean, so I guess it still does come back to the BIM model only being as good as the engineers using it.
I'll just add there, Roger. Yeah. So, like, you know, it's not currently replacing, you know, doing design, obviously, you know, or creating models. There are some tools out there we've been looking at to do things like pipeline routing assessments and looking at all the constraints given to it and identifying optimum routes for pipelines, but, you know, or ducts or what have you, but they're not quite there yet, I would say. Where we would use a bit of AI would be writing the scripts or the different bits of coding that are helping us develop our models, like, you know, creating sheets or creating intelligent title blocks and that kind of stuff. So it's the kind of peripherals at the moment that AI helps with. It's not kind of cutting into the core of what we deliver in terms of actually designing and modeling things yet, anyway.
Yeah, great, thanks. And I suppose that feeds on to, there's another question here about kind of that maybe the expectation around the magic of these models, and I might come to you, Neil, on this one. But there's this perhaps this expectation that we're going to roll AI into these things, going to make everything really quick. But you mentioned the idea of thinking slow and acting fast, taking the time to set the model up. So clients obviously very keen to get going, keen to make a start on their project and see progress. But how do you manage that conflict between the desire to get started and to make progress and the need to take the time to set up the model correctly, identify the issues, and resolve them on the drawing board before you get into the field, and then it becomes a much bigger issue?
Yeah, so I think initially, as you mentioned there, it's how do you prevent it sort of just being rushed off at the start, and it's really initially, if the client really isn't aware, it's trying to inform them of the benefits early on, probably by setting up your BIM execution plan initially and showing what the benefits of these are. I'm really highlighting that if we don't get some of these interfaces coordinated, between our design teams that really we're going to be running into two issues. And sort of just touching on what Paul and Keris were touching on there, I mean, from the civil perspective, we utilize these tools really. A lot of the benefit can be on clash detection, but ultimately it just identifies the clash, while it's really that the people there who are there to resolve those clashes. But back with the client side, I think these tools also really give them better confidence, and having that visual aspect can have its merits. And if you can inform them early on, the client, by showing them what the power that these models can have. For example, on this substation project I shared there, we had effectively 3 or 4 main stakeholders due to the client, the national operator, the data center operator adjacent to the site. Also, we had the power station operator, and then we also had the landowner adjacent to us. So we had multiple different stakeholders, and by utilizing this model, we were able to inform everyone of any interface issues that they would have, or concerns that they had. We were able to bring this to them early, so that they didn't raise their head later on.
Great, thanks. And you mentioned there a BIM execution model, and actually there are 2 questions in here talking about compatibility. So maybe as a final question, I'll come back to you, Paul. But I guess it's both between the different design disciplines, if they have a preference for different maybe versions of the same thing, or different using different tools. But then also where you've got a client that specifies the use of specific tools, and where there's a requirement to integrate with the tools used by other contractors on the site. And how do you manage that? How do you manage that process?
Yeah, well, I mean, the main thing is that it's resolved at the start of the project, which is what BIM is about, So hopefully, now it's not always the case, but clients come with an EIR and they set out exactly what they want, what softwares they want, and what they expect. That's not always the case, though, and it's often up to the delivery team to work together. So, what we would do a big focus on is the first part after a project starts in the ISO 19650 BIM process, which is mobilization. And you all get together, all the different parties who are doing design together. You decide what tools are on. You talk about what common data environment you're on. You're talking about how you share things. How frequently do you meet up? What are the roles and responsibilities in terms of managing the model and doing clash detection? And who is doing what when? That's all part of the BIM execution plan process. And obviously, another big part, and one of the reasons kind of BIM, came about, is to make sure that there's an open source format to share information. So a lot of people are either, Bentley or Autodesk, but there are other tools available. Sometimes files are shared with IFC, Industry Foundation Class, which is an open format that any 3D model made in any software can be exported to and shared together. So that's one way of managing that, kind of using different softwares. But the main thing, which can be difficult, is to get everyone together and agree from the very start. And not only agree what way things are being done and what softwares are being done and formats, etc., but also just test them, because there's no point testing it when you're a month into the project and you realize this isn't really going to work. So we go in there, a digital delivery team or a BIM manager or information manager, go into projects, get everyone together, make sure we've written a good mobilization plan, and actually test those processes. And that includes actually testing, sharing information between each other, bringing in the client into this process. How are we going to provide information to them? Are they happy with that? And it's rare that it's just perfectly smooth. You iron out a lot of issues in that process. So that's that's where the kind of benefit of this approach comes in, and actually following through with it rather than kind of doing it in name only.
Great stuff. Thanks, Paul. And ultimately, I suppose it's still about the people and getting the people together. The tools help, but you still need the people. So thanks very much to the presenters, to Keris, to Paul, and to Neil. Thanks to you all for attending. we're out of time. So thanks very much, and have a good afternoon.